there are 29 questions on this test. I'll take it out of 19. And you're like, oh, okay, Mr. Cole, sounds good, dude. Whatever's clever, man.
All right, so we have two masses, and they are compressing a spring. We release the masses, and they bounce away from each other. The force on them is the same. Where does that force come from?
The spring.
The spring. So does that make sense that the force pushes on them the same amount?
Yes.
Okay. If F equals ma, then that is true. Ignore this over here. Do you see why the following is true? That last thing?
Yeah.
Mass of A times acceleration of A equals mass of B times acceleration of B, because the force from the spring is the same on both of them. Now let's say A was really big and B was really small. How would their accelerations compare?
One greater mass have lower acceleration.
Right. The big mass would have smaller acceleration. The little mass,
Would have great acceleration.
wee. Right. Make sense?
Yep.
Okay.
Or inverse relationships.
Now, we've not really been talking about acceleration so much as we have velocity, because that is a key component of momentum. So, let's substitute this. I'm going to put delta V over T in for acceleration. All right? So I just substituted change in velocity over time right here and right here for each acceleration. How come T gets to cancel? Yeah, the time is the same for both, because that's the amount of contact time the mass is touching the spring, right? The force is applied until the spring has used up all of its energy, and then they go flying off into space. So now what we have is m delta v equals m delta v. That's change in momentum. Now I'm going to simplify it even further. I'm going to say the initial velocity was 0, which makes sense. When I hold these two together, it's at rest, then I release them, they fly off, so the final velocity and the change in velocity are the same. So, well, bam, that is also true. Okay? Now, that's momentum of A equals momentum of B. That's really what that means. So the change in momentum for A is the same as the change in momentum for B. Again, if mass A was really big and mass B was really small, how would their velocities compare?
They'd be opposites. Really big and really small.
Right.
Matching.
So if A is big, velocity would be
Small.
small. If B is really little, the velocity for B would be
Gigantic.
right.
Gargantuan. Hulking.
Oh, look, there it is. Big mass, little velocity. Now, if we use a zero velocity, and this was a collision instead of what this really is more of an explosion, right?
Wonderful.
Instead, now we have a collision, and the same thing is true. Now, the nice thing about this is that you can make the picture perfectly mirror the equation. So let's think about this in terms of momentum without looking. The big reveal will be coming. So big mass times some velocity v, and this little guy is just sitting still. Collision occurs. All of the momentum is then transferred to the little mass, and now the big mass sits still. So this is like pool table physics, right?
Oh, wait, it's like Newton's ball, like drop one.
Yes, it's like Newton's cradle, that's correct. So all of the momentum gets transferred. So the following must be true. You got that? Big M, little v, plus nothing, must equal nothing, plus little m, big V. So in other words, momentum is conserved. That's a pretty sweet and easy math problem, my friends. The picture is reflected perfectly in the equation. Got it? So the mass and the velocity before the collision has to equal the mass and the velocity after the collision. Do you think we need to take direction into account?
Definitely.
Yeah.
Of course, yes. So there are positives and negatives. And as an example, again, you don't have to copy this down. This will be online. Here's one with numbers that's a little bit more complicated. Okay? So I have a 2 kilogram mass moving at 4 meters per second. and a 3 kilogram mass moving at -2. Negative just means backwards or to the left, correct? They collide, and then they bounce off one another. So if you've ever played pool, you've probably you can have a lot of different things happen, right? One ball can hit another and then transfer its momentum completely. They can both collide and bounce off each other. One can overtake it and they can keep going. So you can get lots of different options here. As long as you keep the signs, be conscious of the signs, the equation's the same. So notice I have momentum before equals momentum after. And there are the numbers put in just like the picture. So mass of 2 times positive velocity of 4 plus mass of 3 times negative velocity of 2. Collision occurs at the equal sign, equals 2 times -2. Now this guy goes backwards, plus 3 times v. Could you solve that equation for v?
Yes.
Yes. Intuitively, what are you thinking for this velocity?
Could be about,
Let's find out. 8 minus 6 equals -4 plus 3v. Everybody okay with that? So then we're going to do 2 plus 4, and then sometimes here. Hey, what does it equal? 2. So you were in the neighborhood. Very nice. Can you do problems like this tonight?
We'll find out.
Let us find out. Tonight's homework is 60 number 4. We're a day behind because of the snow day.
Are there going to be rockets in this section?